Hello, my name is Jeff Hittinger. I am the Director of the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. But more importantly for the proceedings today, I am a proud alumnus of the DOE CSGF program and the chair of the Frederick Howe Scholar Award Committee. Dr. Howes managed the DOE's Applied Mathematical Sciences program during the 1990s and was a strong supporter of the DOE Computational Science Graduate Fellowship. The Frederick A. Howes Scholar in Computational Science Award was founded to honor his memory and service to the computational science community. One or two Howes Scholars are named each year from the recent graduates of the program, based on their outstanding leadership, character, and technical achievement. This year, we honor 3 recipients, one 2020 awardee and 2 for 2021. The selection committee is pleased to name Dr. Kelly Kochanski a 2021 Frederick A. Howes Scholar in Computational Science. Kelly earned a PhD in Geological Sciences in April 2020 under the supervision of Professors Robert Anderson and Greg Tucker from the University of Colorado, Boulder. After graduation, she joined McKinsey & Company in Boulder, Colorado as a senior data scientist in climate analytics. Kelly's recognition as a Howes Scholar reflects both her exceptional technical achievements as well as her demonstrated leadership and character. Kelly's doctoral thesis focused on the formation of snow bed forms in the field of advanced quantitative geomorphology. Snow bed forms, which evolve through complex interactions and feedbacks between fluid flow, granular mechanics, and surface evolution, influence the rates of mass and energy exchange between Earth's surface and atmosphere, as they alter the thermal properties, albedo, and surface roughness. Kelly proposed this research area herself and demonstrated an impressive intellectual range in advancing the scientific understanding of it. Building on her undergraduate fieldwork experience in northern India, she braved high winds and frigid temperatures over 3 Colorado winters, gathering observational data on Newott Ridge. Her unprecedented data set led to a groundbreaking predictive statistical classification model of snow bed form emergence. Building on her undergraduate experience modeling ductile flow in Earth's lower crust and developing smooth particle hydrodynamic software, Kelly repurposed the Rescal sand dune code to model snow bed form evolution, incorporating the necessary physical models and algorithm modifications to simulate this new class of geomorphology problems. In her practicum at Los Alamos, Kelly added important surface effects to the MPAS sea ice code, which will benefit the climate modeling community as a component of the Energy Exascale Earth Simulation Model Community Climate Code. Kelly has also distinguished herself through service and leadership to the community at large. She has shown great initiative in pursuing opportunities to build teams and to share her knowledge. Over several summers, she has participated in the Chilean Young Physicist Tournament in Santiago, Chile, and she initiated and ran a similar program for Hispanic students in the Denver area. She thrives on team interactions, often building diverse teams and establishing many collaborations. Kelly recruited and developed both field and computational research experiences for undergraduates, including a group of intrepid students who helped her field experiments on Newott Ridge and 4 summer interns at Lawrence Livermore. She is a sought-after mentor because she takes the time to understand the students' skills and backgrounds and assigns suitable work that challenges them. In addition, Kelly is a talented communicator who brings others along in her inspired presentations and writes with thoughtfulness and insight. She is also an active blogger and top writer on Quora, posting on a broad array of topics in science, academia, and society. Finally, Kelly took the initiative to understand how machine learning could affect climate science and has since become a leader in the climate community on the subject, serving as co-chair for machine learning for the community surface dynamics modeling system effort and on the core team of the Climate Change AI organization's climate science community. Kelly Kochanski is a computational scientist who not only excels technically, but also takes on leadership roles in the scientific community and at the intersection of science and society. She embodies the qualities Fred Howes promoted in all early career scientists.
Good afternoon or morning, and welcome to the 2021 CSGF program review. I'm Kelly Kochanski, calling in late July, and right now I am here to cool off after a record-breaking heat wave that swept across my city of Denver, as well as much of the US for the last couple of weeks. Here in Colorado, we broke heat records across the western half of the state. Right now, the heat wave is ongoing across the Pacific Northwest, where hundreds of people have been killed and thousands hospitalized from Portland to Vancouver by record-breaking temperatures and the dangers of heat stress. We know that climate change is shifting the distribution of extreme temperatures, in particular extreme heat, across the US around the world. My purpose today is to ask whether there's anything that we, as a group of interdisciplinary, computational, mostly high-performance computational scientists and computer scientists, can do about climate change. So if you don't mind, I'm going to finish my talk down here out of the wind. So the first thing to know about solving climate change is that there's not a single solution to cutting carbon emissions and preventing the climate from getting warmer. Carbon emissions in most of the world are spread between a number of different sectors. In the US, for example, seen here, they're spread between transportation, electricity, industry, commercial and residential work, and agriculture, in a more or less even split. So there's not a single fix. Even if tomorrow we moved all of our electricity over to renewable sources, or we made every single car in the country electric, we'd still have emissions remaining. The downside of this is there's not one easy fix. The upside, I think, at least for all of you working on your careers in many areas of impact, is that there are a lot of areas you can work and still have an impact on this problem. The second piece that shapes what we need our solution to look like is time. So mitigating emissions right now is a lot more effective than mitigating them at any point in the future. This is because carbon dioxide is cumulative. Here on the left, you can see several scenarios for different carbon emissions over time. These are called RCP scenarios in climate modeling parlance, but what you really need to know is that the thick red line that's shooting up is the business as usual scenario, where we keep going forward with carbon-fueled growth. And then the green and yellow lines below that are various scenarios where we cut emissions at different points. And what you can see is that carbon is cumulative in the atmosphere. So the longer we wait to cut, the more of it we end up with. The business as usual scenario shows carbon zooming forwards, and the various mitigation scenarios show different totals that we reach by the end of the simulation in 2100 that depend on when we started to cut. In turn, these different amounts of carbon dioxide lead to different temperatures in the atmosphere. Again, here we can see the business as usual scenario running us up towards an 8 degrees Fahrenheit increase, while the lowest mitigation scenario cuts us off at around 2. It doesn't cut us off at 0, however, and if you look back on the left, you'll see that I'm a little bit out of date, and that scenario assumes that we've cut emissions to be almost flat by 2020, which hasn't happened. So that's more or less out of the question now. We've now locked in about 1.5 degrees Celsius of temperature increases. And in all honesty, we're not cutting that aggressively yet, so that number is probably going to keep going up. So no matter what we do in terms of reducing emissions, we're going to have to learn to adapt to living in a warmer world. Anything we can do about climate change involves both mitigating emissions and also adapting so that we can survive and thrive as the climate changes. The good news is that we are starting to hit a lot of breakthroughs in terms of climate change and climate policy. Both the EU and the Biden administration have recently passed new laws using the financial markets as a lever to start pressuring companies to disclose more about their emissions and their sustainability goals. There's a lot of increasing public awareness and decreasing climate denial, driven in no small part by the fact that we're already seeing a lot of extreme events, like the wildfires last year in Australia, and the heat wave that's hitting the Pacific Northwest right now. And finally, we've also got a lot of new data that's enabling us to actually do things in this area that weren't possible even a few years ago. This is thanks in part to climate modeling, which is driven a lot by our Department of Energy, which funds many of the largest climate modeling projects in the world. and Earth observation, with a lot of driving there coming from NASA, as well as private providers working with new satellite data that we didn't have 3 or 5 years ago. So it's a very promising time to be in this area right now. And then coming back to the machine learning part of this, we've also seen a lot of breakthroughs in machine learning. As many of you know, machine learning has been solving problems that recently were impossible in image recognition, in voice transcription, video processing, even numerical modeling. It's been absolutely changing the computational landscape and the limits of what we do and do not think is possible, and in that sense, overriding many areas of computation. There's been a lot of work by the machine learning community and by others to make this accessible to people from different fields. We've got increasingly good open source libraries like PyTorch and scikit-learn, and we've also got a lot of tutorials that are making it easier for people from other fields or other backgrounds to pick up at least the basics of machine learning in a pretty quick manner so that they can start applying it to their work. Collectively, this leads to a lot of opportunities in many areas, and specifically the area of climate change. I'm going to walk through a few of them here, drawing pretty deeply from a paper that I worked on a couple of years ago on tackling climate change with machine learning. And this was a wonderful paper to work on that involved bringing together more than 20 experts from several areas of machine learning, as well as a number of different domains that have to do with climate change, electricity reduction, energy usage, everything that comes back to the climate. So I'm going to go through a little bit of this here, and I'm going to center this on the two parts of the climate change solution that we've seen before: mitigation, or reducing carbon emissions so that we can reduce the ultimate temperature that the Earth reaches, and adaptation, where we learn to deal with it when it goes up anyway. Mitigation includes many areas: electricity, transportation, building and cities, industry, farms and forests, CO2, and so does adaptation, which involves climate prediction foremost, but also social impacts, education, finance, the way we deal with disaster relief. There's a lot of possibilities here, and I'm going to zoom in on 4 of them right now: electricity, transportation, buildings and cities, and my own area of expertise, climate prediction. This is not to dismiss any of the others as lower impact, but just because we only have about 20 minutes here and there's a lot to go through. I'm excited to start this off with electricity systems, because most of what I know here I learned from another CSGF fellow, Priya Danti. She's been working on electricity systems and machine learning for most of her PhD at Carnegie Mellon and has done some phenomenal work, including recently being recognized on MIT's list of 35 innovators under 35 for her work with electricity and climate change. So we have opportunities across the power grid in power generation, power transportation, and also power consumption. A few standout areas for optimization here include forecasting consumer demand so that we can make better use of the mix of variable but low carbon sources that we have, like wind power and solar, and reliable but high carbon sources like coal and oil and gas, in order to get the most optimal mix with the lowest emissions while still providing everyone's power needs. We can also work on improving scheduling and optimizing the electricity system to remove waste in transportation. And we can work on optimizing some power generation systems, like, for example, increasing the controllability of some existing technologies. And we can also work on accelerating entirely new areas, like doing new types of modeling that might speed the development of new techniques for fusion power and propel us towards a low carbon energy, high reliability energy state. All right, next up is transportation. So when we think about transportation and machine learning, a lot of people think about self-driving cars, zoom, 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 taking a nap while you commute to work. It's pretty great, and it's exciting, and it uses a lot of computer vision and controls, and it's also only one part of this picture. There are also a lot of areas to optimize other pieces of the transport system, like the efficiency of the vehicles that we already have on the road and are going to keep for a while. There's opportunities here to design new vehicle shapes, such as using 3D printing and detecting vehicle efficiency. Developing alternative fuels, that's an area that leans more towards chemical and petroleum engineering. Reducing transportation activity, for example, by supply chain and transport logistics optimization. And also shifting transport modes to lower carbon intensity modes like biking and rail rail freight. All right, so when we're not in transport, we are mostly in buildings. I mean, I'd like to be lying on the beach all the time, but in practice, I spend most of my time in bed, in the office, or more recently in my home office in my living room. And all of these areas use a significant amount of electricity, little bits for lighting, a little bit more for appliances, typically a lot for heating and cooling. And these collectively are some of the largest uses of energy in the average American's life after automobile and flight transport. So again, we have a lot of opportunities to improve city efficiency, both in terms of the development of technologies for smart cities, better models of energy usage, design of more energy efficient buildings, and more efficient controls that can take advantage of, say, more sophisticated availability of low carbon intensity power. All right, so now we get into my section on climate prediction. And this is my area of expertise, so those of you who are itching to ask questions, if you can find them in here, that'll be a little bit of a help for me. When we work in this area, we're mostly concerned with adaptation to climate change, helping people make better decisions given what the world is going to do. And this can take a number of forms, like encouraging people to put a building here instead of there, where there are fewer natural hazards, or shaping infrastructure in a way that's more resilient so that if part of it floods, it won't, say, cut off people's access to a hospital. In order to get these kinds of data and make these kinds of predictions, we need to go through a number of stages. Typically, that'll mean figuring out the climate physics, and this is pretty well done, although I did do my PhD in a very small area of this to do with snow. Putting those physics into a numerical model, and there are a number of top groups of climate scientists working here, many of them led by the US Department of Energy. Taking that climate model output, like rainfall and temperature, and turning it into natural hazards, like flooding and heat stress, which is usually done by an additional layer of models. And then finally, turning those insights into something actionable that governments or companies or individuals can actually use to make better decisions about their life in the coming decades. Here, I'm going to be focusing a little bit on the natural hazard modeling and the climate modeling parts of this. And we have a number of opportunities here. I'm going to pick out a few of them from different areas. First, we've got the opportunity to work on high resolution forecasts, which is called downscaling, or in machine learning parlance, sometimes super resolution, where we take climate model output that is typically hundreds of kilometers in grid cell size and scale it down to something that's usable, that's like 1 kilometer or 100 meters, where you can actually say, that's my house, and oh shoot, it's in the floodplain. Should have bought the one next door. There are also a number of places where we can learn the physical properties of the Earth, such as the behavior of the ocean or the behavior of sea ice, that go on to have large knock-on effects on the behavior of the climate around the world. And then finally, there are some areas for hybrid machine learning and physical modeling, of which I think the standout is simulating cloud physics. Clouds are one of the largest areas of uncertainty in existing climate models. They're challenging because they're smaller than the grid cells of the climate models, but they have a big impact on the amount of solar energy that the Earth absorbs that causes it to heat up. Recent work has been done to create machine learning models that emulate really high resolution, really expensive cloud models, and in a low cost way that we can then plug into global climate models and improve those predictions without adding an exorbitant computational cost. I could go into a lot more detail here, but I'm getting a little bit tight on time. So let's move on to the next couple of stages here. Having gone through the opportunities, I want to spend a couple of minutes talking about some of the challenges that we face here. I've pulled out some examples about the barriers to implementing machine learning in climate science, but a lot of these are also going to apply to many other fields, and they're going to be multiplied if you start going from a technical field into a business application. We've got the question of what excites people. Is it the data? Is it the science? Or maybe the revenue potential? Do we have well-defined objective functions or big, broad questions? Do we care about explainability? How do we get credit and advance in our careers? Do we have to publish in journals and conferences? Not publish at all? What about technical parts of our work? What does our data look like? What's the standards for collecting it in our field? How do we format it? If we have existing tools for reading it, what language are they written in? Is that a language that we can implement new algorithms in fluently, or is it going to be a real challenge? I've spent quite a bit of time working with Fortran. One of the big findings from the work that we've done on machine learning and climate change has been that in all the domains we looked at, the most groundbreaking early work has been done by interdisciplinary teams that combine scientists with machine learning experts. And that's almost a good second title for my talk. The real lesson here is on tackling important problems in general using interdisciplinary work. And the CSGF is a really good venue for this, because doing interdisciplinary work is hard, and it's rare to find people who are good at it. You need to learn a substantial amount of material from not just one domain, which in science is already a challenge enough, but two, and have the fluency to bring those together. While I've been in the CSGF, I've worked with scientists who have written novels, physicists who have taught me music theory, people who have made great contributions from ecology to urban planning and transport. I could go on and list a lot of fantastic people that I've met here, but the overwhelming theme is a lot of people who are able to get to a really skilled professional level in multiple fields. And it's just phenomenal to see that in action. And there's so much to learn from within this community. If I were to round my talk out here with a couple of bits of advice for the current graduate students and fellows, I'd start off by saying, say yes to the exciting things that come your way. Maybe that's climate change and machine learning, maybe it's not, that's fine. But you have an extraordinary amount of freedom now to control what you're working on. And it's valuable. Spend it on something good. In my case, that meant having the freedom and the luck to hit the right project and be able to spend 6 months just reading up on machine learning. That's not an opportunity that'll come along often in my career, and it's a fantastic one to have had. Second, embrace your internships and practicums. I know I'm a little bit of a practicum addict. I did 3 at Los Alamos and Lawrence Livermore National Labs, but they were also some of the best parts of my PhD that went a very long way towards developing me as a scientist and a professional. And they also have an incredible boosting effect on your CV that you shouldn't write off wherever you're looking at ending up. Third, you know that code you're thinking you only need to run once? I know you've got it. You're going to send it off to a supercomputer, and it's going to take 2 weeks or 2 days or whatever, but it's going to come back and it's going to be beautiful. You're not going to run it once. I made that mistake a lot. It's always going to come back to haunt you. Test your code. Optimize your code. It's always going to work out in your favor. And with that, thank you all for listening. Any questions?